Hello, class. Today we are going to be taking notes over endothermic and exothermic chemical reactions. I am taking these notes on blank paper so I don't waste printed packet paper. However, you will be taking these notes on page 10 of your packet where it has this heading. In order to take some notes today, you're going to need a few things. You're going to need a pencil. I'll be using a black pen. You're going to need the color red, so you can use a red colored pencil. I have a red-ish marker. I don't know, my red one died. And then you're also going to need green. And then the fourth and final thing you're going to need today is a highlighter for key vocabulary terms. So again, materials you're going to need, you need a pencil, red, green, and a highlighter. Our notes today are going to be broken into two parts because there are two different types of energetic pathways in a chemical reaction. The first type of pathway, we're actually going to flip it from your title. We're going to talk about exothermic reactions. An exothermic chemical reaction, so think exit, is when energy exits a reaction. It is leaving. More specifically, it is any reaction that has a net meaning overall, release of energy. Now, exothermic is one of our key vocabulary terms, so you are going to want to go ahead and highlight that. I'm going to use yellow colored pencil because when you highlight marker, it smudges, but you'll use your highlighter. So that's our first term for today, exothermic, exit. These reactions are really similar to spot because they tend to feel warm. So in our Hindenburg lab, when you guys grabbed that test tube that had magnesium in it and was bubbling and popping, that warm sensation was energy leaving the test tube. As that energy leaves the test tube, it enters your hand, heats your hand up, and what you perceive is warmth. So that energy is leaving the reaction and enters your hand. However, a reaction can be exothermic even if you don't perceive a warm temperature, because we can't touch all chemical reactions. A really good example of this is the second reaction in your Hindenburg lab. When you took that hydrogen gas and you popped it, you blew it up, you combusted it. So this is when you had that test tube. It was tilted upside down, and it was filled with that gas that you produced in the first reaction. You put a match under that test tube, and you heard a big pop. That pop was your sign that energy was leaving the reaction. Exploding out of that reaction, audible to you. Now, the reason I know this is exothermic is because we have to actually look at the bonds and the different elements involved. So we know that the first element involved is hydrogen. We talked about this last class. Hydrogen is H2. We also learned that every fire needs a fuel source which is hydrogen, and it also needs the presence of oxygen. That's why a candle goes out if you put the lid on. Fires can't burn without oxygen. Once you lit that match and you made that pop, you made your product, which was condensation or water vapor. This is our reaction pathway. Our reaction began when those hydrogen and those oxygens started rearranging. So hydrogen, H2, is 2 hydrogen atoms connected by a bond. Oxygen, O2, is 2 oxygen atoms connected by a double bond. And when you light that match and you add that energy, all of those bonds get broken. They get snapped. So instead of organized atoms, we have atomic chaos. The 4 hydrogen atoms that I started with are loose and running around. The 2 oxygen atoms that I started with are also loose and running around. This is not a stable configuration. That's why it took some energy to get there. Let's say we didn't have to add much energy. I added 1 lit match, which is 1 unit of energy. That was enough energy to break all those bonds. However, these atoms aren't going to stay in this soup. They're going to reform into new structures. Specifically, these bonds are going to reform to make water. And when those bonds reform, that energy leaves the system. And we're going to have more leave than we had enter. This loud pop was a lot of energy exiting at the same time. So let's say we have 4 energy units exiting at the same time. This is going to be my energy output. And when I compare this, I can visually see my difference. An exothermic reaction has a small energy input and a very large energy output. I can represent this visually on my reaction. I can also represent this visually on a graph. Graphically, we're going to stick to something that's pretty simple. We're going to be tracking energy as that energy changes over time. And we're just going to look at how it changes. Now, every reaction has to start somewhere. Let's just start in the middle. These are our reactants. This is our hydrogen chilling out and our oxygen hanging out as well. And then I had to take that energy input in order to break the bonds, which means I got to add a unit of energy, but just 1. Which means the total energy level of my reaction is going to rise. However, it's not going to stay there because the next thing that I do is I have an energy output and I'm going to go down 4 units. Which means I'm going to drop clear to the bottom. which is the end of my reaction, which is when I form my water. So either model is fine, but I want you to be familiar with both. Overall, an exothermic reaction is a reaction that has a net release of energy. That reaction is going to feel warm because as the energy leaves, it's going to enter your hand and heat up your hand. The example that we covered in our lab was the combustion of hydrogen gas. I start with hydrogen and oxygen. I add a little bit of energy in order to break the bonds. This is a very unstable configuration, so bonds are going to reform, and the reforming of those bonds means I'm going to release some energy. Anytime I release more energy than I input, I'm going to have an exothermic reaction. And let's highlight this as well because the graph is going to be an important concept going on. Eventually, you guys are going to be making posters to explain different chemical reactions, and one of the things you're going to have to do on there is model the energy systems. You could pick a graph, but you can also pick a reaction pathway model. It's going to be up to you, but I want to make sure you have some options. The other type of reaction that we're going to cover today is everything in reverse. So we're going to use the same vocabulary, the same terminology, the same type of models. We're just going to reverse it. Exothermic was a net release of energy. Endothermic is going to be a net input of energy. So any reaction that has a net or an overall input of energy. And since this is the exact opposite reaction, we're going to do all of our models in reversed. So instead of exothermic, which felt warm, endothermic is going to feel cold. Which means if you put your hand on an endothermic reaction, which we haven't yet, but we will in your next lab, that reaction is going to steal your energy. It's going to take energy from your hand, which means your hand's going to feel cold. Just like if you grab an ice cube, that ice cube takes the energy from your hand and melts the ice cube. This reaction is going to take energy from your hand. That energy goes into the system. So energy leaves your hand and enters the reaction. And just like this was flipped for this, we're going to take this and we're going to flip it. So instead of taking hydrogen gas and oxygen gas and making water, we're going to start with water. We're going to break that water down and make some hydrogen gas and some oxygen gas. And we already know what's going to happen. We're going to start with water molecules, which we've been drawing for ages. And then we got to add some energy in order to break this bond, but these bonds released 4 units of energy when they were formed, which means in order to break them, I need to input 4 units of energy. I need to add a lot. I'm not adding one match. I'm adding more of a sparkler bonfire situation. Okay, so big input to do the exact same thing. Break the bonds, make the atom soup, and then reform some new bonds. Now, reforming these new bonds is going to release some energy, but it's not going to release nearly the energy that I inputted. Reforming these bonds, it only took 1 energy to make. It's only going to release 1 energy when they break. So my reaction pathway model is very different because my input is much larger than my output, which means my graph is going to be flipped. Now, I'm still graphing the same thing. I'm still graphing relative to time, and I'm watching how energy changes throughout that time. I'm still going to start in the middle because I have to start somewhere. But this time, I'm going to start with water. And I'm going to have an input, but instead of 1 energy input, I'm inputting 4 units of energy. That's a lot. So I got to take 4 steps up. So far up, I might end up actually leaving my scale. All that energy breaks bonds. Then I'm still not going to stay at my peak, but my fall's not going to be nearly as big because instead of outputting 4 energy units, I'm only going to output 1 unit, and I'm only going to take 1 step down. Which means my products are going to be fairly high on this graph. My products are going to be clear. Sorry, motion censored lights. Up here off the scale. My hydrogen and my oxygen atoms took a lot of energy to make. So my endothermic graph has kind of the opposite shape. My exothermic graph was overall downhill. If you were riding your bike, this is more downhill than uphill. Your legs would be okay. My endothermic graph would be quite the workout. If you were riding this, your legs would be pretty dead by the time you got to the top of the hill, and going that little baby downhill is not going to give you that much grace. This is a net uphill. Let's also make sure, let's highlight the term endothermic because that's a major vocabulary term. And then let's update both graphs so that they contain the name of the graph. Endothermic graph was our uphill, where an exothermic graph was our downhill. Now, this is a lot of terminology. So, in order to practice with this terminology, you're going to use this in order to complete a worksheet in your packet. Now, some of these words we have previously defined. Some of them were today, some of them were a few class periods ago, but we've talked about all of them. The term exothermic and endothermic, those are from today's notes, which we took on page 10. Now, I expect your definitions to be similar to mine. If you are putting college definitions down on here, I am not taking credit for that. If I believe you did not actually write and understand your definitions, I'm going to ask you, and if you can't explain them, you won't get points. I've defined these terms. Use the definitions that are appropriate for your grade level. Flammable That's a term you should know. We talked about it when we did that Hindenburg lab. It's a term that we've used before when we're discussing lab safety as well. So we should be able to pull that one from our memory. The other two terms, diatomic and bonds, are from the notes that we took last class. So those are the notes that are on page 2. So if you want to pause the video and go ahead and take some time, go and define these terms in your own words using grade level appropriate vocabulary. Nothing from Google, no AI. Use the words and use the work you've already done. We've written out the definitions. Use what you've got. All right. Now, question 6. What function does the initial amount of energy added to a reaction serve? So, what I am asking you here is, this energy input does something. What does this energy input do? Look through your diagram and remember that we read these left to right. So after energy input, look towards the right and see what happened next in our pathways. And if you need to go back and replay this video, you can. Now, you are expected to use a full sentence, but I give you some hints and some tricks. We know we need to mention the words energy and bonds in our answer, and we can use the question in order to start our sentence. So the question is, what function does the initial amount of energy added serve? Our answer can start there. The initial energy input is for ... And then use your notes to finish that sentence. Now, same thing for number 7. Use your notes. Use the terms. We know I need to use the word bonds and energy. And this time, instead of talking about the input, we're talking about the output. So I can flip my same sentence starter. Instead of the initial energy input, I'm going to say the final energy output . And then you're going to finish these. And then the last two questions should all honestly probably be the most straightforward. An exothermic reaction feels warm to the touch. Why might this be? Use some context clues and use our language cues. Any question that contains the word why must contain the word because in our answer. Now, we can actually just restate this and then add an ending. So we could say something like an exothermic reaction feels warm because ... And we can use a similar sentence down here. I contain the word why. My answer needs the word because, but instead of exothermic, I am endothermic. So we might start our sentence with an endothermic reaction. Feels cold because ... And then you will end there and fill out this page. All right, now make sure you actually go back and fill out the page. I'm not taking credit for sentence starters. You need the correct answers here. Full sentences.